So I'm Jiyao and come from Duke University. Today I will present our work characterizing the physical layer transmission errors in cable broadband network. This work is worked with Zhenyu and my advisor Xiaowei. Both of them come from Duke as well. Nowadays, the reliable and high-speed internet access is crucially important in our daily life, especially during a pandemic. I'm very glad here to present our work in person. But I think during the last 2 years, most of us just work remotely. So thanks to the high-speed broadband network we have, so that we have this able to work remotely. Because of their importance, the quality of broadband access networks has always been of great policy concerns. More than a decade ago, the FCC started the Marine Broadband American project. There are many research projects that measure reliability and the performance of broadband networks as well. Packet loss rate is an important quality of service metric for a network. When the packet loss rate in a broadband network is high, it will highly damage the user experience. For example, one previous research shows that if the packet loss rate is larger than 1%, the quality of the voice over IP service will significantly decrease. In addition, TCP throughput will suffer the high packet loss rate as well. For example, one of the most popular TCP congestion control algorithms, Cubic, which is the default TCP variant implemented in the Linux, Windows, and Mac OS, will dramatically decrease the throughput when the packet loss rate is exceeding 1%. However, when previous work measuring the packet loss rate, they did not distinguish the different sources of packet loss. For example, this figure shows the measurement infrastructure used by the Marine Broadband American project. A customized home device sends a UDP request packet to a remote server. Then, this remote server will send a response back to the home device. However, if either the request or the response has been lost during the transmission, this packet will be labeled as lost packet. This packet loss can come from two sources. One is physical layer transmission errors. It indicates the network operation conditions. The other is the network congestion, which is an indicator of how well a network provisions its capacity. However, because previous works use this IP layer measurement so that they cannot distinguish the different sources of packet loss. Separating the packet loss caused by the physical layer transmission errors and from that caused by the congestion is very important. Firstly, physical layer packet loss is a direct indicator of how physical layer infrastructure works, while other metrics, such as the latency, throughput, or end-to-end packet loss rate, are affected by multiple factors. Quantifying the physical layer transmission errors can help diagnose the physical layer infrastructure issues. Secondly, broadband internet connections are increasingly become a public utility. Through continuous monitoring, policymakers can gauge how well the infrastructure is maintained without regulation and may considering a good policy adjustments if an unregulated broadband network leads to decrease the quality of their service. Finally, understand how much packet loss are caused by the physical layer transmission errors, provide us a good insights on the design of the congestion control algorithms and network simulators. So here is our goal. Firstly, we want to understand the packet loss caused by the physical layer transmission errors in broadband networks. Secondly, we want to investigate how physical layer transmission errors affect broadband customer behaviors. Thirdly, we want to analyze the factors that affect physical layer transmission errors. Here is a roadmap of this talk. We will first introduce how we measure the packet loss rate caused by the physical layer transmission errors. We will then introduce a dataset we used and show our results. Due to the time limitation, so we can only show some interesting results. More results can be found in our paper. Finally, we will share the implications and conclude this talk. This work measures the physical layer transmission errors from cable networks, which is shown in this figure. The signal sent by the cable modem, or CM, will first arrive at a fiber optic node, or FN in short. Then the FN will communicate with the cable modem termination system, or CMTS, use fiber. We measure the physical layer transmission errors using the Datasets version 3.0 code word statistics collected from a CMTS. So I will explain what is a code word is. In the Datasets 3.0 standard, when a CM receives upper layer data such as a MAC frame, it will use a Reed-Solomon encoder to encode it into one or more code words. Each code word contains K data bytes and 2T parity check bytes to correct the transmission errors. Then the modem will send these code words to the CMTS, and CMTS will decode them. There are 3 types of the code words. If there is no errors found in each code word, it will be labeled as an unerrored code word. If there are some errors in the code word, but the CMTS can use a forward error correction to correct them, then this code word will be labeled as crackable code word. If there are too many issues that the CMTS cannot correct them, then it will be labeled as uncrackable code words. And after we obtain these counters, we can use the code word error rate to representing the transmission errors. And this is calculated by the number of uncrackable code words divided by the number of all types of code words. So there are 2 settings of code words used in our measurement network: a long code word and a short code word. Unfortunately, due to our data do not provide this information, we cannot separate the long code words from the short code words in our data. However, based on the proportions of the data bytes and the partial check bytes, we can do this estimate that the long code word error rate is less than the average code word error rate, and the average code word error rate is less than the short code error rate. Next, we will introduce the dataset we used. We used 3 datasets in this work. First is proactive network maintenance dataset and trouble tickets, collected by our cooperating ISP. The dataset contains the code word counters collected from the physical layer. We will explain it in details. The second dataset is the FCC dataset, which is obtained from the Marine Broadband American project. We obtain the overall packet loss from this dataset and compare it with our physical layer data. The last one is the IP layer packet loss dataset from the Alone ISP. Our cooperating ISP want to be anonymous, so we call it Alone ISP. So because Alone ISP is not included in the ISP that FCC measured, so we deploy a similar measurement on our cooperating ISP's network in order to build a bridge between the previous 2 datasets. This figure shows how our data was collected from the cable networks. A multi-node server periodically collects the PM data from both CM and CMTS using the SMP protocol. The data collection period is roughly 4 hours. It contains the performance metrics such as transmission power, the signal-to-noise ratio, the number of crackable code words, the number of uncrackable code words, and the number of uncrackable code words. So this data is only available from upstream to us. We also have the ticket data. When a customer met some network-related issues, she will may just report a ticket. This ticket contains several fields, including the ticket reporting time, the problem description, and the ISP action to solve this problem. Here are details of our datasets. From the PM dataset and ticket, we'll obtain them from this 16-month period from 394 FNs. For the FCC dataset, we use the dataset collected from the same period as the PM dataset from 5 different cable ISPs. And for the Alone ISP, we only collect it from this very short time period, so it is not overlapped with the previous 2 datasets. All the devices are cable devices that are able to respond to ping requests. Next, we will highlight a few interesting results. This figure shows the complementary CDF of the code word error rate among all data points. The x-axis is the code word error rate value in log scale, which we computed using this formula, as we mentioned before. There are 3 lines shown in this figure representing the 3 upstream channels, respectively. We can observe that the channel with higher frequency have a lower code word error rate. We can also observe here, nearly 1% of the data points have the code word error rate larger than 1%. Since the distribution of these 3 channels are similar, so in the rest of this work, we will combine the 3 channels together and only show the results for the channel combined cold-water error rate. Next, we check the average cold-water rate distribution among different FNs. For each FN, we calculate its average cold-water error rate among all the devices inside this FN for the entire data collection period. From this figure, we can observe that there are nearly 1% of the FNs whose average loss rate, cold-water error rate, exceeds 1%. We define these FNs as unhealthy FNs. There are 12% of FNs whose average cold-water error rate is between 0.1% to 1%. We define them as alarming FNs. Finally, more than 87% of the FNs have a cold-water error rate lower than 0.1%. We define them as the healthy FNs. Here, the 0.1 and the 1% thresholds are recommended by our cooperating ISP. From this figure, we can see that the cable network can suffer high physical layer packet loss that exceeding 1%. This figure shows an example of the FN with highest average cold-water rate in our data. From the first 6 months of this figure, the average cold-water rate of this FN is around 7%. And for the following 7 months, although the average cold-water rate decreased, it is still around 2%, which supported our previous conclusion that wired network can suffer high physical layer packet loss. Next, we will estimate how many packet losses are caused by physical layer transmission errors. First, we compare the measurement results of the FCC dataset with along ISP's IP layer dataset. The purpose of this comparison is to understand whether along ISP's quality of service is similar to the cable ISPs that FCC measured. This figure shows the distribution of the overall, which is IP layer average packet loss rate for each devices on both FCC measurement and along ISP measurement. We can observe here, the along ISP's measurement results have a wide range. We think that is because the along ISP's measurement including 19,000 devices, while the FCC only measured 1,000 devices. So from this figure, we find that these 2 measurements have a similar distribution. Then this figure shows a packet loss distribution among different ISPs. We can find that the along ISP's packet loss distribution is similar to the Comcast, Charter, and Optimum. The previous and this figure show along ISP's cable network is representative. Therefore, our hypothesis is that the physical layer data measured in along ISP is also representative to the cable ISP's FCC measured. So we can use a cold-water error rate measured in the along ISP to answer how many packet losses are from the physical layer. This figure shows our estimated results. Since the FCC measurement only uses small packet, so 1 packet will be encoded into exact 1 short code word. So we can approximate that the value of the packet loss rate with the value of the cold-water error rate. The purple bar here is the physical layer packet loss that we compute from the healthy FNs only. The blue bars here are the FCC and along ISP's IP layer packet loss rates. And this blue line estimated how many packet losses are from the physical layer for each ISP. So from this figure, we can see that at least 12% to 25% losses are from the physical layer. This is a lower bound estimate for several reasons. But for example, one reason is that our physical layer measurement only collects the data in the last mile, which is only 1 hop. However, the FCC's measurement, the packet will go through more hops. Therefore, comparing to the FCC data measurement, our physical layer loss rate is underestimated. There are several more reasons for this lower bound can be found in our paper. Therefore, our conclusion is that the packet loss caused by the physical layer is not negligible. Next, we will show how the cold-water rate affects customer behaviors. We checked whether customers will report more tickets when the cold-water error rate increased. To quantify the customer tickets reporting behavior for a specific range of the cold-water error rate, we define this ticketing rate as the number of the tickets divided by the total time. The y-axis of this figure shows a normalized ticketing rate, which means we use the ticketing rate for a certain range of the cold-water rate divided by the overall ticketing rate. From these 3 bars, we can observe that in healthy FNs, customers report much more tickets when the code word error increases. However, for the right 3 bars, we can find that customers in alarming and unhealthy F1s will report much less tickets compared to the customers on the healthy F1s, indicating that those customers have a higher tolerance to the packet loss. Due to a time limitation, I will ignore one result, and then we will just go to the final implications and conclusions. Firstly, wired network can suffer from high physical layer packet loss. We witnessed that some fiber optic nodes may have a physical layer code word error rate persistently higher than 1%. Secondly, we estimated that at least 12% to 25% packet losses in cable ISPs that the FCC measured are from the physical layer. Thirdly, customers in high-loss F1s have a high tolerance to packet loss, so the absence of the tickets do not equal to the absence of the network issues. The ISPs may not only rely on the customer report tickets as the network fault indicators. Finally, projects that measure the packet loss rates in cable broadband networks should use different packet lengths, since the packet with different lengths may be encoded into different numbers and types of code words and experience different physical layer packet loss. So we will release a subset of the PM data via this Git repo. If you have interest in this data set, please feel free to check it out. Thanks for listening, and I'm glad to answer questions.